Welcome everyone. So glad to have all you students and parents joining us aaj session May. Today, we're diving straight into a really fascinating journey. We're going to translate real-world problems into the timeless, what I like to call Lindy language of mathematics. Now, what exactly do I mean by Lindy? Well, it basically means these math concepts have truly stood the test of time. They're these ancient, super robust tools of logic that are just as powerful for understanding our universe today as they were centuries ago. I mean, really think about it for a second. कैसे X and Y हमारी real-world problems solve कर सकते हैं? How can simple letters magically act as keys to decode everyday life? Honestly, it kind of sounds like a magic trick, right? But it's not. It's just pure, beautiful logic. And by the end of this explainer, you're going to see exactly how we can take a messy, super complicated real-world situation and organize it perfectly, just by using a few letters and numbers. Here's the roadmap for our translation journey today. First, unpacking algebraic expressions. Second, defining linear polynomials. Third, the math input-output machine. Fourth, linear growth and decay. And finally, number 5, graphing on a plane. All right, let's jump right into part 1, unpacking algebraic expressions. Let's start with something we've all done, a simple shopping trip. Imagine our friend Raju goes to a stationery shop. The shop owner tells him, hey, the red boxes have 4 pens each and the blue boxes have 5 pencils each. So Raju decides to buy X number of red boxes and Y number of blue boxes. And, as a bonus, he gets 3 extra pens absolutely free. So if we look at the total number of items he has, it's 4X plus 5Y plus 3. Do you see what just happened there? A regular, everyday shopping trip literally just became a mathematical expression. Now, let's break this expression down piece by piece so every single concept is perfectly defined. In Raju's shopping haul, the 4x, the 5y, and the 3 are what we actually call the terms of the expression. You can think of them as these distinct individual building blocks that are just glued together by the plus signs. Next up, let's look at those letters. The x and the y are our variables. I like to think of them as empty containers. Because we don't know exactly how many boxes Raju decided to buy, these values can change, right? वो बदल सकते हैं. Hence the perfect name for them, variable. But what about the numbers attached to those letters? Well, the 4 and the 5 are our coefficients. A coefficient is simply the fixed numerical factor that gets multiplied by the variable. So in our shopping story, it represents the fixed amount of pens or pencils inside each respective box. You know, the number of boxes Raju buys might change, but the number of pens inside a single red box, that is always 4. And finally, we have the 3. This little guy is our constant. And why is that? Because Raju got 3 free pens no matter what else he bought. Literally, even if he buys 0 boxes, he still walks out with those 3 pens. Ye value हमेशा fixed रहती है. It constantly remains a 3 no matter what. Okay, let's test this out with another really concrete example. Imagine a rectangular garden. It has a length of L and a width of W. And let's say the total cost to fence and seed this garden is given by 200L plus 160W plus 50LW. So looking at that, can you identify the terms, the variables, and the coefficients? Let's do it together. The terms are 200L, 160W, and 50LW. The variables, our letter numbers, are L and W. And the coefficients, those fixed multipliers, are 200, 160, and 50. Moving on to part 2, defining linear polynomials. So to classify these mathematical tools, we use something called the degree. The degree is simply the highest power of the variable in a polynomial that just has one variable. It's kind of like looking for the highest rank in an army to know exactly who's in charge of the equation. When a polynomial has a degree of 1, meaning the variable has no visible exponent and is just to the power of 1, we call that a linear polynomial. An example would be 3z plus 7. But if the highest power happens to be a 2, like in x squared plus 5x plus 1, well then it becomes a quadratic polynomial. But don't worry about that one right now, because for our explainer today, we are keeping things strictly linear. Now, what exactly happens when we set a linear polynomial equal to something else? We get what's called a linear equation. For instance, if I tell you the sum of 2 numbers is 64, and one is 10 more than the other, we can write that out as x plus, in parentheses, x plus 10 equals 64. That simplifies nicely to the linear polynomial 2x plus 10, equating to the constant 64. And suddenly, it's a puzzle we can actually solve. We just subtract 10, divide by 2, and we find that x equals 27. It's almost like magic. Let's step right into part 3, the math input-output machine. So, I want you to imagine this for a second. Agar मैं एक factory machine हो तो क्या होगा? Seriously, what if every formula is basically just a machine on an assembly line, just sitting there waiting for raw materials? Imagine we have this polynomial machine called 2x plus 3. This is what we call a dynamic function. If our input, our x, is 4, we just drop it into the machine. The machine multiplies it by 2 to get 8, adds 3, and spits out an output of 11. Simple, right? If we drop in a -6, the machine goes to work again. 2 times -6 is -12, plus 3, giving us an output of -9. The beauty of this is that every single input has a very specific, totally predictable output. Which brings us to part 4, linear growth and decay. Because these math machines are so incredibly predictable, we can actually use them to forecast the future and track changes over time. When we use linear polynomials to track time, we generally see 2 main patterns. First, linear growth. This just means a quantity increases by a constant fixed amount over equal intervals of time. Linear decay is the exact opposite. The quantity decreases by a constant fixed amount over equal intervals. The key takeaway here is that it's steady, it's totally reliable, and it never ever randomly jumps around. Let's look at a real-world example of this, a draining water tank. At month 0, the starting point, the water height is 3 meters. In month 1, it's 2.5. Month 2, it's 2. Are you noticing the pattern yet? The height is dropping by exactly 0.5 meters every single month. Because this decrease is constant, it is an absolutely perfect example of linear decay. And because it's so predictable, you can easily figure out that at month 5, the height will be exactly 0.5 meters. And finally, we arrive at part 5, graphing on a plane. This is where everything comes together in the ultimate Lindy formula for a line, y equals ax plus b. No matter what numbers you plug in for a and b, if you graph this equation, it will always, and I mean always, draw a perfect straight line on a graph. So here's how you decode it. The a is your slope, which basically represents how steep the line is. Are you climbing a steep mountain or are you walking on a completely flat road? That steepness is your a. Now the b is your y-intercept. This is exactly where your line cuts across that vertical y-axis. It's essentially your starting point. And here's a really fun fact. If b is exactly 0, your line passes straight through the very center of the graph, the origin at 0, 0. Ekdam straight. So as we wrap up this explainer, I want to leave you with one final thought. क्या आप एक x और एक y से universe के और भी राज खोज सकते हैं? Think about it. If a simple linear polynomial can effortlessly predict the exact water level in a tank months from now, or instantly calculate fencing costs for a garden, what other incredible mysteries of the universe could you solve with just an x and a y? The tools are literally in your hands now. Keep exploring, keep translating our complex world into the beautiful language of math, and thank you so much for joining me on this journey today.